Hi, this is a brief video on molecules as we make our way through the beginning parts of chemistry. I'm following Brown, Burston, LeMay, and Murphy's Chemistry, the Central Science. But again, any chemistry textbook is going to cover this material very early on. So what are molecules? So molecules are basically two or more atoms that are tightly bound together. They are, as it were, a package of atoms. So we're talking about if we're taking the Legos of life and adding them together, different Legos fit together and different atoms fit together. They bond together, we say. So a molecule is a package of atoms that you can package it that way. It fits together. Only the noble gases like to travel alone. So the noble gases, as we'll find out, are so stable in the way that they're structured that they don't need friends. They can go off to the wilderness and contemplate the deeper things of life. Neon doesn't need any friends, and so noble gases are the only real parts of the periodic table that like to be just all by themselves. There are also diatomic molecules like oxygen, O2. Since it's the beginning of a chemistry course, that O2 there means that there are two oxygens that are stuck together. So there are some atoms that like to travel with their Siamese twin. They like to travel with their identical twin, as it were. And oxygen's one of these. So in nature, you do find O2, H2, N2, and the halogens are in group 7, if you remember. Things like fluorine and chlorine. And so you do find, you don't find oxygen all by itself usually, a lone oxygen. You tend to find oxygen in its diatomic form, two oxygens glued together, or two hydrogens glued together, H2, or two nitrogens glued together, N2, or two fluorines glued together, F2, or two chlorines, Cl2. So these are the ones that like to be by themselves with a friend. Then there are all the rest, the molecular compounds like water. Water has two hydrogens and one oxygen glued together. These are molecular compounds. So basically molecules are packages of atoms that you can buy at the store. And here we're talking about in nature. Of course, in the lab, we could do all kinds of fun stuff. But whenever we refer to oxygen in chemistry, usually we're talking about O2. Or whenever we refer to hydrogen, we're usually referring to H2 because that's the form it takes in nature. By the way, H2O, O2, these are called chemical formulas. The salt, that's called a subscript. The 2, in both cases, is a subscript. It means two of them, but the two go together. There's a difference between putting the 2 in front of the O or in front of the H. If you have two O2s, then you have two molecules of oxygen. O2 means that it's a package that goes together as a package of two oxygens. Okay, chemical formulas. Now, molecules mainly have to do with nonmetals. That is the right side of the periodic table. The next video I'm going to make is on ions, which tends to be the way metals relate and package, as it were. So we tend to talk about molecules when we're talking about non-charged particles, non-ionic particles. More on that to come. But basically, for now, just remember that we tend to speak of molecules when we're talking about non-metals. Okay, empirical formulas. There are two ways to the formulas that I've just been talking about are called molecular formulas because they give the exact number of atoms that bind with the exact number of other atoms. So like O2 tells us that oxygen gas likes to travel as two oxygens glued together. There is another kind of formula called an empirical formula, which basically gives the simplest ratio between different types of atoms. Let me give you an example. So H2O2 is hydrogen peroxide. If you have a little owie, you might pour a little peroxide on your toe, or whatever, and it fizzes up, and it's all very fun and occasionally painful. But anyway, so H2O2 is the molecular formula for hydrogen peroxide. But if I were to give the empirical formula of H2O2, it's just a HO. hydrogen, oxygen, that's the empirical formula. That is taking the ratios down to their smallest number. You don't have fractions, by the way, in these formulas. It's just multiples of 1. And so HO is the empirical formula of hydrogen peroxide. Now you might ask, why would I ever want that? That doesn't give me that much information. Well, sometimes when we're doing an experiment, the result basically comes out in ratios. And so having a name for the simplest ratio between things is useful when we are doing experiments, and that's the result we get. We're going to need more information to get from the empirical result, as it were, the experimental result, to the actual molecular formula. We'll need more information. So that's one reason, is because sometimes when we do experiments, we end up with what in effect is an empirical formula, simple ratios. Then there are other things like carbon. Carbon actually forms these extensive networks of carbon to where you can't. It's almost impossible to actually say this is the core molecule. And so having a basic empirical formula can come in handy there. So there are places where empirical formulas come in handy, although most of the time we're going to want to talk about the actual molecular formula. Okay, finally, this section talks about structural formulas. And I'm sorry, I'm trying not to use other people's work, so I used the old hand. But a structural formula basically gives you a sense. It's not precise, but it gives you a sense of what of a drawing, as it were. So here's 3 different ways of picturing H2O or water. And water does tend to be that kind of bent structure, but this is not in any way precise. So you have a structural formula where you just have the letters and lines between them. The lines represent what are called bonds. More on that to come. Ball and stick model is like you might find in a classroom. The teacher has a little ball and stick, like Legos for atoms. Ball and stick model. And then a space filling model doesn't have the bonds. It just kind of shows them clumped together. So there are some 3 different ways. There's also a perspective model that Brown, Burston, LeMay, and the other one, Murphy, talk about. But I didn't draw that. Okay, well, this has been a brief introduction to molecules.